I wondered if you would just start by giving a summary of what this found.
This result was from a series of observations as part of the JWST Early Release Science program that was looking at transiting exoplanets, so those planets that happen to pass in front of their host stars along our line of sight. And this particular planet is a planet called WASP-39b that orbits a star very similar to the Sun. It's about 300 Kelvin cooler than the Sun. The planet itself has a radius larger than that of Jupiter, which in turn gives it a radius of about 14 times that of the Earth, while the planet's mass is only a third that of Jupiter, or about 89 times the mass of Earth. So the combination of this very large radius relative to Jupiter, but then also small mass relative to Jupiter, means that it's actually got a very low density. And this in turn makes its atmosphere very puffy. And so this makes it a good target to observe exoplanet atmospheres, because essentially there is more light that is being blocked by the planet's atmosphere while it transits across the face of its host star. The planet is on a very short orbital period. It's very close into its host star, and this in turn means that it has a very high temperature of about 1100 Kelvin. And the other thing about this planet being so close to its star is that we expect that it's tidally locked to the star, which essentially means that it completes one rotation on its axis in the same length of time that it takes the planet to actually orbit the star once. So it's the same as in the Moon-Earth system, where the Moon is tidally locked to the Earth and we always see the same side of the Moon. So this planet has one permanent day side, which is always facing the star, and one permanent night side that's always facing away from the star. So if you basically think, then that means that essentially the day side is continuously bathed in this stellar radiation, while the night side is continuously not bathed in that radiation. And so this in turn leads to this really large temperature gradient between the day side and the night side. And in turn, from theories of atmospheric circulation, we would predict that this temperature gradient combined with the rotation of the planet would lead to a super rotating equatorial wind within the planet's atmosphere. And essentially what this wind would do would be to carry hot day side gas to the night side and cold night side gas to the day side. So since this wind is going essentially in one direction, what you would in turn then expect is that at the hemisphere of the planet where the day side gas goes to the night side, then that hemisphere should be hotter than the hemisphere where the night side gas is being carried to the day side. And because of the way that, for example, clouds or the evaporation and condensation point of clouds is, of course, temperature dependent, then you would expect perhaps to see differences in the clouds and what molecules happen to be in the gas phase at the one hemisphere compared to the other hemisphere. And so essentially that's what we've been able to measure. So what I did was to develop a new technique to independently measure the hemispheres of the planet's atmosphere. So the hemisphere that is where the day side gas is being carried to the night side gas, we would call that the evening side. And then the hemisphere where the where the night side gas is being carried to the day side gas, that would be the morning side. And so as the planet passes in front of the star, if you imagine the planet passing in front of the star from left to right in your mind, then as the planet's first passing in front of the star, you only have light that is filtering through one side of the planet's atmosphere, the right-hand side in this situation. And if the planet is rotating in the same direction that it's orbiting, then that right-hand side is essentially the morning side, where the night side gas is being carried around to the day side. Conversely, when the planet is starting to leave the face of the stellar disk, then the light from the star is preferentially passing through the left-hand limb of the planet, which in this case would be more sensitive to the evening side, where the hot day side gas is being carried to the cool night side. And because JWST data is so precise, you can essentially fit these small portions of the transit and ignore the part of the transit where the planet is entirely in front of the star. And that allows you to independently measure the morning side from the evening side spectrum. And what we actually measured was that the evening side is indeed hotter than the morning side by about 177 Kelvin. And that in turn, this hotter temperature leads to larger amplitude spectral features on the hotter evening side compared to the cooler morning side. So for example, we've detected things like water and carbon dioxide in this planet's atmosphere before. And what we've now seen is that the amplitude of, in particular, the carbon dioxide feature varies between the hotter evening side and the cooler morning side, which we believe is due to a combination of the different temperatures between these two sides of the planet's atmosphere, combined with the fact that there would be likely different cloudiness or degrees to which the morning side is cloudier than the evening side.
Why do we want to know that? Why is that interesting to know?
Well, it's interesting to know because we have no equivalent to these sorts of planets in our solar system. So Mercury has an orbital period of about 80 days, while the majority of transiting exoplanets that we detect are actually about 10 times closer in to their stars than Mercury is to the sun. So this is basically an entirely different temperature regime to that which we have in the solar system. And given that the majority of known exoplanets to date are at these very short orbital periods, then we want to understand what impact these close separations to their stars have on the planets and their atmospheres. And as I said previously, from a theoretical point of view, we expect that this tidal locking and these very hot temperatures would drive these super-rotating planetary winds. And we've seen evidence for this in previous observations. But this is the first time that we've been able to directly measure the morning spectrum and the evening spectrum of a planet over a wide wavelength range. And this is quite different to the way that we would previously interpret a planet's transmission spectrum, so the spectrum that we measure while the planet is passing in front of the star. Because previously we would essentially assume that the atmosphere of the planet is homogeneous. And when we are measuring the starlight that is filtering through the planet's atmosphere, we're essentially measuring a globally averaged atmospheric spectrum rather than previously measuring the difference or measuring the morning spectrum independently of the evening spectrum. So this allows us also to test predictions about how, for example, cloud coverage would differ between the morning side and the evening side. Essentially, we're testing and measuring weather in an exoplanet's atmosphere.
It's amazing to think of weather, that you can know something about weather on something so far away. So, I mean, I imagine things cannot live on these planets, but if you could kind of look at the morning side and look at the evening side, what would each look like?
So that's right. So in this particular case, this planet is far too hot and too large to be considered habitable. But what we see evidence for is a larger degree of gaseous carbon dioxide at the hotter evening side than at the cooler morning side. And what this is probably telling us is that there is some species that is condensing out of the hotter day side gas as it passes into the night side gas and is leading to a larger amount of clouds on the cooler morning side than the hotter evening side. So I suppose if you were in orbit around the planet, then you may see greater cloud coverage at the cooler morning side than the hotter evening side.
Now that you've been able to do this, are there other planets you want to look at to make sure that the result matches up, or is there other things you want to look at in planetary atmospheres that you can now do with JWST?
Yeah, so our plan next is to, one of the things that we'd like to do is to analyze the same planet but over a wider wavelength range. So the results that we're presenting so far are from a single instrument on JWST that covers a wavelength range from about 2 to 5 microns. But JWST has actually observed this planet with several different instrument modes, covering a combined wavelength range of about 0.6 microns in visible light to about 15 microns in the mid-infrared. So one thing that we would like to do is to apply these same techniques, but to the other instrument modes for this same planet, where we will be sensitive to different molecules than just those that we are focused on in this 2 to 5 micron wavelength range. And of course, what we'd also like to do is then apply these techniques to a much broader set of planets, covering, for example, different temperatures, different masses, different radii. Because we've now demonstrated the feasibility of this method with JWST, and the precision of JWST is so immense that it really opens up this new avenue into understanding and measuring atmospheric circulation for exoplanets that we were previously largely insensitive to. I guess one thing I would like to make clear is that there were other techniques that we used to analyze this data that were complementary. So, for example, the lead author approached the problem in a slightly different way. So rather than just fitting the ingress light curve independently of the egress light curve, which is what I did, the lead author's approach was actually to fit the entire light curve, but assuming that the planet actually has 2 different radii. So rather than being a single circle, you could imagine it as being 2 hemispheres essentially with slightly different radii. And so in that way, he is able to fit the entire transit without just focusing on the ingress portion and the egress portion. And essentially what we find is that our 2 approaches are very complementary and result in the same conclusions.